Okay. Today we're going to find the limit as x approaches 9 of x minus 9 over root x minus 3. That's our first one for the day. What should we do first?
Plug in 9.
Good. We have not forgotten that. So this should be 9 minus 9 over root 9 minus 3, which, lo and behold, comes out to be
Indeterminate.
0 over 0. So
0 over
indeterminate.
0 or indeterminate. Yep. Bummer, which means we got to do some extra work. So we got two different ways we're actually going to go about this one. It's going to be great. I'm going to make I made like a big giant T in the middle of the thing, and we're going to do this two different ways. What color? Should we use red, blue, green? What should we use?
Blue.
Blue. All right. So one of the ways we're going to do it is how. Somebody tell me how we're going to do this. How we're going to turn this into something that's not indeterminate, something we can do. Don't all say stuff at once.
You could multiply the bottom by square root x plus 3.
Okay, what do we call that?
I think it's like the conjugate where you flip the sign.
That's exactly what it is. So the first method we're going to use here is we're going to multiply by the conjugate. And the multiplying by the conjugate, you probably learned about it last year, the year before, or back in like 3rd grade or something, is a way to get rid of these radicals, right? If you multiply by the conjugate of a radical expression, it clears out all of the radicals. It effectively turns it into like a difference of squares. So that's what we're going to do. We're going to start with the limit as x approaches 9 of x minus 9 in the numerator, because that's still x minus 9. And we're still going to have a root x minus 3 in the denominator. But we're going to multiply both the top and the bottom by root x plus 3, which is the conjugate of the radical expression. And we don't only use this for radical expressions. Sometimes we use multiplying by the conjugate with like trig expressions too. That can be helpful from time to time, but it's especially helpful with radicals. So this ought to become the limit as x approaches 9 of x minus 9 times root x plus 3. Don't need to do anything with that. But in the denominator, root x times root x is
X.
Yeah, and 3 times root x is 3 root x. And negative 3 times root x is negative 3 root x. So those will cancel. And negative 3 times 3 is negative 9. And now we have some terms that cancel out. And we'll probably note that since this is a limit as x approaches 9, it'd be really nice to cancel out the x minus 9 terms, because those are what's making it 0 over 0. Oh, we were supposed to do this in blue, and now I've switched to red. All right. The limit as x approaches 9 of now just root x plus 3, or root 9 plus 3, or 6. Everybody good with that?
Yep.
Spectacular. Yeah, multiplying by the conjugate. Super, super great way to evaluate some of these annoying limits with radicals in them. All right, let's take green here. What's another way we could have done this? Anybody see a different way that might have even been a little bit quicker and simpler? I'll give you a hint. It's what we did yesterday to deal with indeterminate limits.
Break down x minus 9 into square root of x plus 3 and square root of x minus 3.
Exactly. We could just factor out that numerator, that x minus 9. Well, x minus 9, that's just it's not in like a form that we're used to looking at for a difference of squares, but it is. Basically, any binomial with a minus sign between them can be a difference of squares. Right? I just take the square root of the first term and add the square root of the second term, multiply it by the square root of the first term minus the square root of the second term. That should not have, I don't know why there's like a little extra mark there. Fix that. And then that ought to cancel with that root x minus 3 in the denominator. Everybody good with that?
Yep.
Cool.
Yeah.
And so that's our limit as x approaches 9 of root x plus 3. And I just did that one, so I'm not going to write out all the other little intermediary steps. So the one intermediary step I did, it's 6. Good or no? I have no preference whatsoever which way you guys decide to do this. Doesn't matter to me. Just know both methods. There's other methods to do it too, but we don't quite yet have the skills to use those other methods. Someday we will, but not today. Cool. Let's do another one. This is one of the new slides that I added. Root x minus 2 over 4 minus x. The limit as x approaches 4. Okay, so before I force you to try to do this one on your own, what's the first thing we should do?
Plug in 4.
Yeah, that gives us root 4 minus 2 over 4 minus 4, or 0 or 0. So we're definitely indeterminate here. So I will give you guys about a minute or two to see if you can simplify this down in some way. So that you can evaluate this limit that is indeterminate. So you might want to multiply by the conjugate. You might want to do some factoring. There might be a little bit of additional stuff you have to do to it. But I have so much faith in all of your abilities, even though I've only known you for one day. So take a minute and see if you can do that. So you could have chosen to factor your denominator, or you could have chosen to multiply both numerator and denominator by the conjugate of the numerator. So we'll just do the conjugate way since we've done a bunch of factoring problems the other day. So this should become the limit as x approaches 4 of root x minus 2 times root x plus 2 over 4 minus x times root x plus 2. And then your numerator ends up becoming what? Should be x minus 4.
Mhm.
And then we got 4 minus x in the denominator with that root x plus 2 also. And we don't have anything that cancels out immediately, right? Because x minus 4 is not the same thing as 4 minus x. But if we were to factor a negative out of one or the other of them, it doesn't really matter. We'll do it out of the numerator. So negative, that gives us a 4 minus x, right? The negative 4 turns into a positive 4, and the positive x turns into a minus x. And now those ought to very nicely cancel out those 4 minus x's. And we just end up with the limit as x approaches 4 of negative 1 over root x plus 2, which we can now evaluate, negative 1 over 2 plus 2, or negative 1/4. Is that what you all got?
Yep.
Yes.
Cool. No issues with that? Any questions or any problems or anything? All right, and we could have factored it, right? We could have factored the 4 minus x into 2 minus root x and 2 plus root x. But then we would have still had to factor a negative out. But same answer either way. All right. Let's move on to a different type. So let's look at the limit as x approaches 0 of 1 over x plus 4 minus 1/4 all over x. What should we do first?
Plug in the 0.
Plug in the 0, which gives us 1/4 minus 1/4 over 0, or 0 over 0, right? Another indeterminate one. This time we have a complex fraction, right? A complex fraction is just a fraction that has other fractions within it. Call those complex fractions. So any thoughts on how we want to find the limit of an indeterminate complex fraction? Because these show up often enough.
You could try to get rid of the denominator by multiplying everything by x.
Okay, so you want to get rid of the denominator of the x. Okay, so that's a way we could start this off. We can't multiply. Okay, I see what you're saying. Multiplying everything by x. Well, let's do this. I think you have the right idea. Let's take this x over 1 that's in the denominator and just multiply. This is just a fraction. Right? This is just something divided by a fraction. So I can just multiply that something by the reciprocal of this. Do you all agree with that? I could make this, the limit as x approaches 0 of 1 over x times 1 over x plus 4 minus 1 over 4.
Yeah.
Yeah. Okay. Well, wouldn't it be nice if I could combine these two fractions together into one? I think that'd be good. So how could I do that? I just need to get a common denominator between the 1 over x plus 4 and the 1 over 4. So that will give me a limit as x approaches 0 of 1 over x times 4 over 4 times x plus 4 minus x plus 4 over 4 times x plus 4. Good or no?
Good.
Cool. And then if I wanted to, in the next step, I could combine these two fractions together, which would give me 4 minus the quantity x plus 4, which we'll distribute through in a second, over, well, let's see, if I'm multiplying 1 over x by this whole thing, I could just bring that x into the denominator, so 4x and x plus 4. How do we feel about that?
Good.
Good. All right. Simplifying the numerator gives us what? 4 minus x
X,
minus 4.
a negative X.
Yeah, it's going to give us a negative x over a 4x times an x plus 4. And we have some common terms here. We have an x and an x. So we'll cancel those out, giving us a limit as x approaches 0 of negative 1 over 4 times x plus 4, which ought to be negative 1 over 4 times 0 plus 4, or negative 1 over 16. Good or no? Questions on that, or everyone okay with it?
Wait, I'm confused about where the 4x came from.
Okay, so we had this right here, right? The 4 over 4 times x plus 4 minus the x plus 4 over 4 times x plus 4. Are you good with that part?
Yeah.
Okay, so we have the 1 over x on the outside of it.
Oh, I see.
Right, so we just multiplied that x into it.
Yeah.
Cool. Any other questions or issues with that one? All right, here is another complex fraction one. Why don't you guys take 1 or 2 minutes and see if you can work through this one on your own again. Make sure that you see that it's indeterminate first before you actually go through trying to solve it. I'll give you guys a minute to work on that. All right, let's go through and do this one all the way through. So 1 over x plus 2 plus 1 over x plus 3, as x approaches negative 3, becomes 1 over negative 1 plus 1 over 0, which is 0 over 0. So we always want to remember to check that it's indeterminate. But now that we can see that it is, we'll go through and simplify the complex fraction. So I know in that first one, we multiplied by the 1 over x plus 3. Before we kind of wrote it up there before we simplified the complex part of it, before we simplified the numerator. This time I'm going to just wait and do it after we've simplified it. So we got the limit as x approaches -3, and the common denominator of 1 over x plus 2 and 1, right? 1 is just 1 over 1. That common denominator ought to be x plus 2. So we're going to get an x plus 2 over x plus 2 up here. And I'm still going to write this as just over x plus 3 for now. So we got a limit as x approaches -3 of, if I combine these together, that's 1 plus x plus 2, which is x plus 3 over x plus 2. And then as we said, we can multiply this by 1 over x plus 3 by the reciprocal. And that will allow us to cancel out the x plus 3's, giving us a limit as x approaches -3 of 1 over x plus 2, or 1 over -3 plus 2, which is -1. Any questions or issues or concerns about these simplifying complex fraction ones? Okay, so you'll have definitely some of the rationalizing ones and some of these complex fraction ones on your homework tonight. You'll also have something even more unpleasant that looks more like this. The limit as x approaches 0 of the cube root of x plus 27 minus 3 all over x. What should we do first?
Plug in 0.
Plug in 0. We got the cube root of 27, if we plug in 0 for x, minus 3 over 0. Cube root of 27 is, unfortunately, 3. So we end up with 0 over 0, another indeterminate one. So, any thoughts on how we will deal with this one? It sort of looks like the ones where we rationalize part of it, right? Right, with a root and then a plus or a minus some constant. But unfortunately, the rationalization there only works for square roots. And sometimes you can kind of work around it with other even roots, but this is an odd root. And so unfortunately, multiplying by the conjugate isn't going to do us any good here. Anybody see any nice factoring to do there? Those are the two methods we sort of know, right? There's not a complex fraction, so we don't need to simplify the complex fraction. And the multiplying by the conjugate's not going to work. What about factoring? You guys see a way to factor something or no? Nah, me neither. I assume by your silence that you don't see a way to factor that. So we're going to have to do something else. Any idea what else we might do? No? No ideas? All right, let me ask you a quick question. Have you ever solved an equation that looked, let's say, like this? X to the 4th minus 5x squared plus 4 equals 0. I hope the answer is yes. How do you
Yes.
solve it? How do you solve that?
You use a variable in place of x squared.
All right, right. We let u equal x squared, right? And then this becomes u squared minus 5u plus 4. And then you factor it and so on, right? And once you get back down to the end, you go back and replace things into the x's and do all that, right? But we do a substitution, right, to make this simpler to factor. Yeah. Yeah, that's what we do. So let's think about that same idea. What piece of this is the most irritating part of it, probably?
The cube root of x.
Yes, this cube root of x plus 27 is kind of a pain. So let's just get rid of it. Let's let u equal the cube root of x plus 27. Yeah, why not? Cool. Let me write that in there. I've now got the limit as x approaches 0 of u minus 3 over x. Well, this just looks kind of like a bunch of garbage now, right? I've got a u and I've got an x. I got multiple different variables, and I'm only looking at when x is approaching 0. So what am I going to do about that?
Can you substitute the x with a u-term?
That sounds like a great idea. So if u is equal to the cube root of x plus 27, that tells you that u cubed would equal x plus 27 if I cube both sides, and that x would equal u cubed minus 27. Everybody good with that? Just rearranging our little u substitution. That's something that we're going to want to get used to this year, is making u substitutions and then rearranging that substitution to substitute out some other junk. So now we've got a limit as x approaches 0 of u minus 3 over u cubed minus 27. Well, that still seems like a problem, right? Because I have a limit as x approaches 0 of something that's all in terms of u. Seems like it'd be better to have the limit as u approaches something, wouldn't it? Right. What do? We plug in the 0 for x, so there's no x's to plug it in for, right? So as x approaches 0, what does u approach?
Three.
Should be approaching 3, right? 0 plus 27, cube rooted is 3. So we should then be able to write this as the limit as u approaches 3 of u minus 3 over u cubed minus 27. And that looks a whole heck of a lot better than what we started with. And so now all we got to do is plug in 3, right? 0 over 0. Still indeterminate, right? That's a problem. But luckily, at this point, what can we do? We should be able to
Factor out a u minus 3 from the denominator.
Yeah, we'll factor out that denominator to cancel out those u minus 3s. And so this is one of the reasons that you should know how to factor a difference of cubes. I'm just going to assume that you all know it, even though that's a real dangerous assumption. And we'll end up with u minus 3 over u minus 3 times u squared plus 3u plus 9. We'll cancel the u minus 3s to get the limit as u approaches 3 of 1 over u squared plus 3u plus 9. Or 1 over 3 squared plus 3 times 3 plus 9, which is 1 over what? 9 plus 9 plus 9? 1 over 27. Good or no?
Good.
Awesome. Any issues or questions with that one? All right, here is another one. I say we work through this one together, unless you guys really want to try it on your own. You guys want to try it on your own or no?
Together.
Together, all right. So we've got the cube root of x plus 8 squared minus 4 times the cube root of x plus 8 plus 4 all over x squared. Well, what should we do first? Put in our 0, right? Cube root of 8 is 2, and 2 squared is 4. And then here we've got 4 times the cube root of 8, so that's 4 times 2, so minus 8, plus 4 over 0 squared is just 0 over 0. Yeah. A little bit unfortunate there that that's indeterminate. It would have been really cool if that one had just worked out to be a number. So what's the most annoying part of this?
The cube root of x plus 8.
So let's get rid of it. U equals the cube root of x plus 8. So that's going to leave me with a u squared minus a 4u plus a 4 in the numerator. And this time I'm not going to spend time with each step of converting the denominator and converting the value that we're approaching for a limit. I'll just do it all at once here. So this tells me that x is equal to what? Ought to be u cubed minus 8. So x squared ought to be, well, that would be u cubed minus 8 squared. And as x approaches 0, what does u approach?
2.
2. Just plug in 0 for x there, you get 2. So as x approaches 0, u approaches 2. So this limit is, the limit is u approaches 2 of u squared minus 4u plus 4 over u cubed minus 8 squared. And now we'll factor things out. We could plug into 2, but you'll find if you plug into 2, it's still 0 over 0. So the limit is u approaches 2 of u minus 2 squared in the numerator. And what is u cubed minus 8? It should be u minus 2 times u squared plus 2u plus 4. And if I'm squaring that, then both of those ought to get squared. And what can we cancel? Yeah, u minus 2 squared over u minus 2 squared, giving us the limit as u approaches 2 of 1 over u squared plus 2u plus 4 squared. Plug in your 2. And you get 1 over 144. Good or no?
Good.
Spectacular. All right. That is what your homework tonight is going to be on, is these 3 different ways of simplifying some limits down to be able to evaluate them. There'll also probably be a couple more of just the ones where you plug it in and don't get something that's indeterminate. There'll also probably be just 1 or 2 where you just factor as well. So this is what your homework will generally look like tonight. But we're going to continue moving on from there and talk about a few other important things with limits. So we're going to start by looking at a couple of limits that don't exist. We haven't really had any of those yet. So we're going to show that the limit as x approaches 0 of 1 over x doesn't exist. And this is going to be pretty easy. What does the function 1 over x look like? Does it have anything in the first quadrant? Yeah, it
Yes.
should look something like this, right? And what about in the second quadrant? Is there anything in the second quadrant for it?
No.
No.
What about the third quadrant?
Yeah.
Yeah, just the mirror image of this across the origin. So pretend like I did that really nicely and it looked like a mirror image of it. What about the fourth quadrant? fourth quadrant's a mirror image of the second quadrant, right? Okay. So why doesn't the limit as x approaches 0 exist? Well, what's going on with this graph? First, we have a horizontal asymptote at y equals 0. And second, we have a vertical asymptote at x equals 0. And if I have an asymptote and my function is approaching that asymptote, it tells me that 1 over x is either increasing or it's decreasing. And we call this without bound, meaning that it increases so rapidly that it goes towards infinity before it makes it over to 0. And it decreases so rapidly that it goes towards negative infinity before the x values hit 0. It increases so rapidly that it can't effectively move over to all the way to this x equals 0 value. That's what approaching one of these vertical asymptotes really means, right? That it's increasing or decreasing without bound. And if it's going up towards infinity or going down towards negative infinity, is there a real number that we are approaching?
No.
No, from one side of this, it's going down towards negative infinity, and from the other side, it's going up towards positive infinity. Neither of those are real numbers, right? Infinity is not a real number. And so we are not approaching any real number value. And so therefore, this limit does not exist. And because there's no real number, didn't mean to do that. There's no real number that we are approaching. Good or no?
Good.
Excellent. All right, cool. So let's look at another one. The limit as x approaches 0 of sine of 1 over x. Now, you're probably thinking the sine of 1 over x. I don't know what that looks like, right? Because you probably never dealt with the sine of 1 over x before. So let's graph it in Desmos. Here it is, the sine of 1 over x. Isn't it great? Looks like it's got a horizontal asymptote, right, of y equals 0 that it's approaching. True? But we're interested in what's happening to this function as x approaches 0. Well, the other day when we looked at sine x over x, remember looking at that? We looked at sine x. And we were like, oh, it looks like it's approaching 1, right? And we zoomed in sort of a little and saw that nothing weird was happening there. Remember doing that? Hopefully. Well, let's do that now. Let's zoom in around x equals 0 and see what's happening. Can you tell better what's happening now?
Not really.
No, not really. How about now?
No.
How about now?
No.
Zooming in and not really, right? Let me just keep zooming in here. It just sort of looks like some sort of endless little like corridor that we're like stepping into some sort of alternate dimension or something. I don't know what we're doing, right? But it gets a little bit smashed together there, right? And it looks like we might guess that this function is oscillating back and forth from 1 to -1, up to 1, down to -1, up to 1, -1, 1, -1, over and over and over and over again. Just, I mean, a whole heck of a lot of times. True?
Yes.
Yeah, it does look that way. So how can we be sure of what the limit is? We need some sort of algebraic method to figure that out. Because we don't know if we zoomed in far enough. Maybe if I kept zooming in far enough, I wouldn't end up with just this giant red block, but somewhere in the middle here, maybe they'd stop oscillating up so high. and maybe they'd be getting closer to 0. Or maybe they'd be getting closer to 1. Or maybe they'd get closer to -1. It's kind of hard to tell, isn't it? Because there are some functions, like this one, I'm going to put an X in front of that, where if I zoom in on them, that looks like it's oscillating back and forth, doesn't it? But at the same time, those oscillations, the heights of those oscillations are getting a lot smaller, and maybe we are approaching 0. Well, maybe that happens with this one, and we just haven't zoomed in far enough to be able to see it, right? Do we think that's happening? Or no? What do we think? You guys all just like completely lost?
No idea. No, I have no idea.
No idea what we're doing, or no idea what the answer to my question is?
The answer to your question.
Ah, okay. All right. So let's think about this. If we wanted to prove that this limit didn't exist, could we perhaps prove that it goes all the way up here to 1 and all the way down here to -1 and back up to 1 and down to -1 an infinite number of times as we approach 0? Because if it keeps going up to 1 and back down to -1, well, then there's certainly no way for it to be getting smaller and narrowing out to some value of 0, right? And it sure looks like, it sure looks like it's going up to that value of 1 up here, right? An infinite number of times. And it sure looks like it's going down to this value of -1 an infinite number of times. So all we got to show this limit doesn't exist is that this function hits 1 and hits -1 an infinite number of times as we go towards 0. Sounds easy enough, right? Huh. When does this function hit hit y equals 1? When does the sine of 1/x equal 1? And when does the sine of 1/x equal -1?
Infinity.
Well, let's try it a different way. When or what angle does sine equal 1? Because our angle, right, our angle is 1/x. So if 1/x was equal to the angle that when you take the sine of it gives you 1, that'd be a time when this function hits 1, right? So what angle when you take the sine of it gives you 1?
Over 2.
Supposed to still be seeing Desmos?
Oh, are you still seeing Desmos?
Yes.
Yeah.
Sorry, I started writing other stuff. Maybe that's why people got more confused. All right, so sorry, thank you for telling me that. So the sine of 1/x equals 1 when the angle 1/x equals pi/2. Are there any other angles when sine is equal to 1?
Yeah, there are infinitely many.
There are an infinite number of them, right? Every 2 pi times any integer. Right, because pi/2 it equals 1, and then the sine of 5 pi/2, which would be when n is 1, and the sine of 9 pi/2, which would be when n is 2, or even let's say -3 pi/2 when n is -1. All of those work. Right? What about over here with the sine of 1/x equaling -1? Well, that would be true when the angle is equal to what? What angle gives 3 pi/2 plus 2 pi n also. And if we wanted to figure out what the actual x values for this were, we just take the reciprocal of each side. Same over here. Oops. Got my one over for a second there. And then let's plug in some integers and see what happens. If you plug in 0, what's the first value that you get? You get 1 over pi over 2, which is 2 over pi. And if we plug in n equals 1, this is 1 over 5 pi over 2, which is 2 over 5 pi. And then the next one, if I plug in a 2 for n, that's going to become 4 pi or 8 pi over 2, so 9 pi over 2, or 2 over 9 pi. Next one's going to be 2 over 13 pi, then 2 over 17 pi, and so on. What about over here? 2 over 3 pi. And then if I add 2 pi to that with n equal to 1, it's going to be 2 over 7 pi, and then 2 over 11 pi, and so on. And what can you tell me about the numbers and the relationship between 2 over pi and 2 over 5 pi? Which one's bigger?
Isn't 2 over pi bigger?
2 over pi is bigger than 2 over 5 pi, right? Right? Because, I mean, let's just estimate pi being 3, even though we know it's not. This is about 2/3. This is about 2/15. This is about 2/27, right? These numbers are getting smaller as we go and put in more values of n, right? These are getting smaller. And what are they going towards? What are they getting closer and closer to? The denominator is getting bigger, but the numerator is staying the same. So they're getting
Closer to 0.
Yeah, they're getting smaller and closer to 0. So there are an infinite number of these times, right? Because there are an infinite number of integers, right? 2 over pi, 2 over 5 pi, 2 over 9 pi, 2 over 13 pi, 2 over 17 pi, 2 over 21 pi, 2 over 25 pi, and so on. That just goes on forever, right? And they're getting closer to 0. So it hits hits y equals 1 an infinite number of times as we get closer to 0. And the same thing here. These are getting smaller and also closer to 0. So there are an infinite number of times when it hits 1 and an infinite number of times when it goes back down to -1, which means that it cannot be narrowing out to any number between those values. Does that make sense?
Yeah.
The graph's oscillating back and forth from -1 to 1 to -1 to 1 to -1 to 1 more and more frequently as we get closer to 0. There's no chance of it approaching a specific value. And so we would say that limit doesn't exist. Wasn't that exciting?
Yeah.
Yeah, that was pretty exciting. Now, let's think about this just for a second. These values that I wrote out were only positive values, weren't they? As were these ones. True? Positive values, positive values.
True.
And normally when we look at a limit, we look at what's going on from both sides, don't we? Now, don't worry, I'm not going to make you do any more work with this. But if n was -1, that would give us a negative value down here, wouldn't it? It would give us -2 over 3 pi, and then we'd have -2 over 7 pi, and -2 over 11 pi, and -2 over 15 pi, and the same general concept over here. And those numbers would be getting closer to 0 as well. And so we could look at it from both sides there. And it's important for us to start to think about this concept of looking at limits from each side. And so we're going to talk now, just for a minute before we get finished up today, about what we call one-sided limits. One-sided limits are either left-hand limits or they are right-hand limits, where we only care what's happening to that function as we approach a from the left, or the notation from the negative side, or we only care what's happening as we approach A from the right or from the positive side. Now, all the same rules still apply with these one-sided limits, except that for our two-sided limits, for all these limits we've been doing, that they're officially called two-sided limits, but we just call them limits. We had to have, part of the definition was we had to have some interval. I'm going to just real quickly go all the way back to the beginning. We had to have some interval on both sides of A, right? And we were approaching it from both sides. Well, when we talk about a one-sided limit, I'm not going to care about this. I'm going to say what happens as I approach A from the left. I don't care if there's anything over here. My function could have ended and there could be nothing there. Or I'm going to say what happens as I approach A from the right, and I'm not going to care about anything to the left. Conceptually, is that okay?
Yeah.
Cool. So as long as we have an open interval to the left, we can do a left-hand limit. As long as we have an open interval to the right, we can do a right-hand limit. So let's take a look at a function and see if we can find right-hand limits and left-hand limits, and also a two-sided limit, one that doesn't have a plus or minus on it for this function. So we're looking at f of x equals radical x minus 2. So let's first draw our graph real quickly. Should have something about like that. Yeah, just a sketch, but it should be about like that, yeah? Should be familiar with radical functions. So let's think about the first one. As x approaches 2 from the right. As I approach 2 from the right, what y value am I getting very close to?
0.
0. Easy. What about as I approach 2 from the left? Is there a function over here?
No.
Right? This is not in the domain. And if I have a section that I'm trying to find a limit of, but there's no continuous portion of my function over here, it's not in the domain, this limit cannot exist. Good or no?
Yeah.
All right. What about the limit as x approaches 2 of f of x, the two-sided limit? Do I have an interval on both sides of it?
No.
No, and so this two-sided limit also cannot exist. I think it might be sort of intuitive here to think about what relationship do we need to have between the left-hand limit and the right-hand limit in order for the two-sided limit to exist.
They have to be the same?
They have to be the same, right? If the left limit and the right limit are not the same, or if one doesn't exist, then the two-sided limit will also not exist. So our rule that we've just sort of stated is the limit as x approaches a, which is the two-sided limit of f of x, equals some number L, if and only if the limit from the left and the limit from the right both equal L. So you can't have a two-sided limit unless the left hand and the right hand both exist and have the same value. Good or no?
Good.
All right. Now, we are almost done. We're going to do one last problem. It's going to be quick and easy, and then we're going to quit for the day. So, I think I already have this sketched in the PDF I put up there, but absolute value of x over x looks just like this. True? I think I had that sketched in the notes for you. This is a graph you want to get used to. You want to get used to like the little iterations of it, like absolute value x minus 2 over x minus 2, just shifted to the right 2 units, but otherwise the same. So what's the limit as x approaches 0? Here's x equals 0, right? The y-axis. As x approaches 0 from the left, what is our y value? Very, very close.
-1.
equal to -1. And what about from the right-hand side?
1.
1.
And what does that tell you about the two-sided limit?
Doesn't exist.
Yeah, they're not equivalent on both sides.
It's not the same on both sides, so that two-sided limit does not exist. And that is where we're going to stop for today. Tomorrow, we're going to come back and we're going to redo this problem, except we're going to redo it algebraically and show algebraically why this is true as well. Anybody have any questions on anything we've done so far today?